Hi, everybody, and welcome back to MTED 110. Today we're doing lecture 11B. So we're going to continue with chapter 11. Let me go ahead and pull up the slides. Let's get started. All right, so last time we were talking about, what was it? Activity 11A. Oh, that's right. Factors, multiples, primes, and composites. So today we're going to start talking about divisibility. I actually thought that this was going to be the long lecture, but the one with a lot of slides, but I think this one's actually going to be relatively short. Today we got to talk about a little bit about divisibility, but before we can really start talking about divisibility, we have to learn some divisibility theorems, which we'll talk about in a minute here. So first, let's talk about what's called a prime factorization. You've seen this before. Prime factorizations are what you get when you do like a factor tree for numbers. We're going to see that in just a moment too. But let's start here. The fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says that every integer greater than 1 is either a prime number or it can be represented as a product of prime numbers. Moreover, the representation is unique except for the order of the factors. So this is really amazing because what it tells you is that any whole number that you can think of, any whole number, it can be written as a product of prime numbers or it's a prime number itself, which is pretty amazing, I think. Also, whatever that representation of prime numbers is, it's unique. So there's only one way to do it, except if you want to like commute the factors around. That's it. um, Oh yeah, there you go. So what this tells us is that the prime numbers are like the building blocks for all natural numbers greater than 1. And that's really why we like prime numbers so much. Every number is built out of prime numbers. Yeah, there you go. I just said that out loud. And here's a good example. The number 288 can be written as this product right here, 2 times 2 times 2 times 2 times 2 times 3 times 3. And notice that 2 and 3 are prime. So every factor in that product is a prime number. And we like to just group all of the repeat factors and use our exponential notation right there. So the number 288 is the same as 2 to the fifth times 3 squared. And that's all you need. So if you want to make the number 288, you're going to need 5 factors of 2, and you're going to need 2 factors of 3. All right. Yeah, so this thing right here, this is what's called the prime factorization of 288. And we're going to see how to do that in just a minute here. Every number has a prime factorization, and that's what the fundamental theorem of arithmetic says. This is kind of a restating of the fundamental theorem of arithmetic. There you go. Oh yeah, so one thing to note, it's convention to list the prime factors in ascending order. So for example, 2 comes before 3. So we want to write them in that order. Wait, I should probably go like this, right? Write them in ascending order. So 2, 3, 5, 7, 11, and so on. It just makes it easier because what we're going to do is we're going to use these prime factorizations and start comparing them to get information about the numbers themselves. This is just my little tip. One way to determine a prime factorization is just to start dividing away, or I shouldn't say dividing away, subtracting away, repeatedly subtracting, dividing by the smallest possible prime every time. And I think I have an example of that coming up right here. Yeah. So this is a prime, this is a factor tree for the number 2100, 2100. And you can write 2100 as 2 times 1050. So what I did here was I just recognized that this was an even number, and so I divided by 2. And then this new number, 1050, that's also an even number, so I divided by 2 again. And then I divided by 5 when I got to 525 because I know that's divisible by 5. Why is that though? Why is that divisible by 5? Hmm. That's a good question. We're going to see that in the next lecture. And that's one way you can proceed. That's the idea. And then to find the prime factorization, what you do is you basically just pick out all of the leaves, all the leaves that are sticking out here. And that's what I've got right over here. So if you basically select all of those leaves, this is going to be your prime factorization. All those numbers are prime. They're as small as they can possibly be. And if you multiply them all together, then you're going to get the number 2100. So this is it written in a more concise form. And again, notice that the numbers are ascending, right? The prime factors are ascending. 2, 3, 5, 7. One thing I want to emphasize here is that this is not the only way to do a factor tree, and this is not the only way to find a prime factorization. You just have to divide this number by any number that you know it's already divisible by. So let's try to do a different example. Let me go back here so we can compare two different factor trees. So what I'm going to do instead, start up here, 2100. I see that that's 21 times 100. So I'm going to factor it like that. There we go. Now 21 is 3 times 7, and 100 is 10 times 10. And that's 2 times 5, and that's 2 times 5. And then what I'm going to do is I'm going to go ahead and pick out all the leaves, right? There we go. There we go. Those are all my leaves. I'm just circling them. And if I collect them all, I see that I've got, oh, what is it? 2 squared, right? There's two twos right there. There's a 3. Oops, that's not a 3. There's a 3 right there. There's 2 5s, so I need a 5 squared, and then there's a 7. So that's the prime factorization. And I think that's what we had on the next page, right? Yep, there it is, same thing. So just keep in mind that you can factor these in any way that you want. For me, because I tend to get overwhelmed sometimes by large numbers and dividing them, I just tend to go for the smallest prime that I can think of. But you can do it whichever way you would like. Okay, so here's an interesting question from a student. So let's pretend that your student Francisco thinks he's found a contradiction to the fundamental theorem of arithmetic, and he shows you the following two factorizations. He says, "Oh look, this is the same as this," and the fundamental theorem of arithmetic says that that factorization has to be unique. And so my question is, has he found the contradiction? Go ahead and take a minute and think about it. Okay, so now that you've taken a minute and thought about it, go ahead and speak out loud. What did you think? What were you saying? Or sorry, what were you thinking? Say out loud what you were thinking. All right, let's take a look at these. So the first clue that he probably has not found a contradiction is that the theorem that he thinks he's contradicted is called the fundamental theorem of arithmetic. And usually if a theorem starts with the word fundamental, it's probably one of the most important theorems in that entire field. So I highly doubt that he's found a contradiction, but don't believe me, right? Who says just because I don't think that he has? Why would I? Don't believe me. We should be able to verify that he has or hasn't. Like I was saying, this is mathematics, and this is what we got to do. We got to prove these things, right? So he hasn't found a contradiction because this number right here, 14, is not a prime number. 14 is actually 2 times 7, right? And once you factor that as 2 times 7, you'll realize that you can change this to a 5 and this to a 5, and this number will disappear. And then you'll have the exact same factorization that you have on the left side, or the left side. All right, so no, he has not found a contradiction. But that just goes to show that you need to completely factor. You have to factor all the way if you want to find a prime factorization. And if you don't, then your prime factorization is not going to be accurate. Okay, so here's a question, and this is kind of leading us into uh, why we like prime factorization so much. How many factors does 72 have? That's the question. How many factors does 72 have? How could we possibly tell? Remember, factors are numbers in a product, right? So, I mean, I know I could write 72 as 2 times 36, for example. So I know 2 and 36 are factors. 1 and 72, obviously, are factors. But the question is, how many of these factors does this number contain? How is there a way for me to tell, right? Well, the first thing we're going to do is we're going to find its prime factorization. So let's do a factor tree for 72. And like I said, I like to go for the low-hanging fruit, so I'm going to say 2 times 36. Oh, but I noticed 36 is 6 times 6. And that's 2 times 3, and that's 2 times 3. Now let's go ahead and collect all of these leaves. There we go. All of those are prime. There's no way for me to divide anymore. And then my prime factorization is going to be, let's see, 1, 2, 3 twos. So 2 cubed. And then 1, 2, 3s. There we go. Let me give myself some more space. There we go. So 72 is the same as 2 cubed times 3 squared. So if you wanted to build the number 72, you're going to need 3 factors of 2 and 2 factors of 3. This is also one of the reasons I was saying that understanding what a factor is so important, because I'm going to start using that word a lot, and it's important to know what I'm talking about. So this is the prime factorization. Oops. This is the prime factorization right here, and we can use that to figure out how many factors there are. And the reason is because these exponents here are essentially encoding how many of each building block we need. And so if you tweak those a bit and multiply them together, multiply the bases together, you'll see that we get another factor each time. And so I have a little table here. The table goes like this. So first, let's just consider these factors. That's the number 1, right? 1 is definitely a factor of 72. But then 2 is also a factor. This is the number 2, right? 2 is also a factor of 72. And then here, this is 4. 4 is also a factor of 72, as it turns out. And then this is 8. 8 is also a factor of 72, right? 8 times, oh geez, it's one of those ones. Is it 8 times 9? I think it's 8 times 9. Yeah, it's 8 times 9 because 8 times 8 is 64. And then 8 more than that would be 72. Yeah, so 8 times 9 is 72. See, that's why you got to have this type of knowledge so you can figure it out on the fly. Um, anyway, so if you look at this top row, the idea here is that first we started at 0. And we started at 0 just because we need to account for the factor 1. And then all I did was increment or increase one of the exponents, and I held the other exponent fixed. Okay, and that'll give us a set of factors. And then I did the same thing for 3, right? So now, or sorry, I incremented the exponent for 3, and then I cycled through the exponents for 2 again. And that gives me a set of 4 more factors. And then the same thing here. I incremented the exponent of 3 to 2, and that's the last one, and then cycled through the exponents for that factor of 2 right there. And we get another set. So that means that there are 12 factors. Now, the thing about this is that the factor tree was not really sufficient to give us that. You can actually get all those numbers out of there. Like, for example, 2 times 6, that's 12. That's a factor. That's a factor of 72. Why is that? Because we know that the product 2 times 6 is in this number, right? Let's go back. Here it is right there. It's in that number, right? That product is within the prime factorization. So we know that it is actually a factor itself. But you can see that having to do all of these having to do all these like pairings, like that's not a factor actually. But doing all these like various pairings to try to find what factors are, it's going to get really, really complicated, right? That's why the prime factorization is so nice. Because if you have the prime factorization, then you can always generate this table. And if you can generate that table, then you can find not only what all the factors are, but how many of them there are, right? So we're going to focus more on this table and prime factorizations. But again, I mean, what if my number has a lot of, what if my number has a long prime factorization, right? What was the one that we did previously? It was this one. Like this one's a little bit longer, right? So I have to change the exponent for all 4 of those numbers. It's going to be a bigger table, and that can get pretty messy as well. Well, remember the question that we were asking ourselves is how many factors that number has, how many factors it has. So now that we have a systematic way of figuring out what all the factors are, let's just figure out if we can use this to find out how many factors there are total, how many there are. And I offer this example. So look at this for a minute and think about it and see if you can determine a pattern from what we saw a moment ago and what you see here. Hmm. Hmm. So what do you think? Do you see a pattern? You might not be able to see it because it's a little bit tricky, but 5,000 has 20 factors and 72, which is, where did it go? I should say, actually, shouldn't highlight that. Let me highlight this. This has 20 factors, and 72, which was 2 cubed times 3 squared, this one has 12 factors. And think about this table again. Remember this table, the way that we generated it was by cycling through all the powers, right? But we had to include this 0 exponent as well to account for the factor 1. So what do you think now? Hmm, what do you think? Well, here's the trick. All we have to do is increment the exponent and multiply that result together, all the exponents, and that'll tell us how many factors there are. So in this case, 3 plus 1, that's 4. 4 plus 1, that's 5. And 4 times 5 equals 20. That's the number of factors. That's it. So with 72, which was 2 cubed times 3 squared, what we would do is we would increment each of those. And so we would multiply 4 times 3 to get 12, which is how many factors 72 has. So that makes total sense, because if you think about it, remember multiplication can always be represented as an area? Well, this table is kind of like an area. And here's one of those blocks, and here's another one, and here's another one. How many of these blocks do you see? Oh, what's that? Is that a 3 by 4 rectangle? Yes, it is. It's a 3 by 4 rectangle. And the reason it's 3 by 4 is because we had to account for these zero, I should use a different color here. We had to account for these zero exponents. Zero exponents. So it's not just 3 times 2 because we need to account for those zero exponents. If you only do 3 times 2, you're only going to be catching that part of the table. So that's the idea. You got to increment it up 1. So that's the general idea. So if you want to find the number of factors, you increment the exponent in each prime factor and then multiply that result. All right? And I can do more examples of that in the collaboration meeting if you're interested. Just ask. Okay, so now we're going to start talking about divisibility. So now we have an idea of what primality is and prime numbers, and we know we can determine how many factors a number has. Let's talk about divisibility. And my first question is this: is this number 495,687,115 prime? Think about it for a minute. Hmm. Okay, so I'm pretty sure everybody was like, no, it is definitely not prime at all. And how were you able to tell that? I'm guessing most of you saw that there was a 5 at the end here and said, oh, well, it ends in a 5, which means it's divisible by 5, right? That's a writing divisible really poorly there. Divisible by 5, right? But why is that true? How did you know that? Who said? Do you believe them? What if they're wrong? What if they're just leading you on? That's a very interesting thing, because what you're saying is that you can tell that this number is divisible by another number, 5, just by looking at a numeral in its representation, which is interesting because it's like you're using the numerals to determine divisibility of a number, which is interesting. So the question is like, why is that true? Okay, how about this number? Is this number prime? Take a moment to think about it. What do you think? All right, yeah, that one's not prime either, right? That one's not prime because it ends in a 6, so it's an even number, which means it's divisible by 2. But again, how do you know that's true? Why is that true? Why can you just look at the last digit and suddenly you know all about this number, right? Or at least you know something about this number. That's very peculiar. I don't believe anybody that tells me they can do that. I want proof. And we're going to get that proof in the next lecture. Wait, sorry, in the next lecture. um, yeah, there you go. With these two, you can probably tell right away the answer is no. We have several divisibility tests, and that's what we're going to learn. But that's going to be the next lecture. So first, we need to develop our understanding of divisibility. And this is where things are going to get a little bit technical. So the following content is actually not in the book. And I'm kind of disappointed about that because our previous book had this content, and our current book uses these theorems without actually outright stating them. So I think it's important to go through them for our own edification so that we don't have to just take somebody's word that these divisibility tests are true, for example. Um, so first, this is in the book, but the definition of an even number. This is a definition that you do need to have memorized. You need to have this memorized. You need to know the definition of an even number. And here's the definition. A number is even if you can write it in this form: n equals 2 times k, where k is some whole number. Another way of seeing that is that a number n is even if it has a remainder of 0 when you divide it by 2, right? So if you divide something by 2 and it goes in there evenly, or equally, I should say, then it must be an even number. But really, this is the kicker right here. Any even number can be written in this form. Any even number can be written in this form. And that's how you prove that a number is even. You write it in that form. And it's going to seem trivial at first, but let me show you an example. I know that, for example, 14 is an even number because I can write it as 2 times 7. So in this case, 7 is k. So k equals 7 in this case. That's how I know 14 is an even number. Or for example, how about 1026? I know that that's an even number also because I can write that as 2 times 513. There we go. That's what makes it an even number, the fact that you can write it in that form. So if something says, if you see a question that's like prove something is even, this is what you have to do. That's what you have to do. All right. Now, in contrast, an odd number is similar, but in this case, it can be written in this form, n equals 2k plus 1, plus 1. You could also say minus 1, but we'll say plus 1 just because it's a little bit easier in this context. Equivalently, an odd number is a number that has a remainder of 1 when you divide it by 2. So if you divide it by 2, 2 doesn't fit in there equally. It's always got a remainder of 1 at the end. That's what it means to be odd. Okay, so let's do an example. I happen to know that the number, hey, here we go, 15 is an odd number. Why? Because I can write it as 2 times 7 plus 1, right? That's 14 plus 1. And in this case, this is what k is. K is 7. So notice the structure is identical here. The structure is 2, 2 times k plus 1 plus 1. That's how we know 15 is an odd number by definition. Let's see. How about the number 1237? Whew. Okay, gave myself a somewhat hard one. Let's see. I can write this as 2 times 618 plus 1. Is that right? Let's see. 2 times 600 is 1200. 2 times 18 is 36. And then that, yep, that'll give me 1236 plus 1. There you go. See, that's why you have to know all that stuff about our numeration system from before, right? Okay, so again, the structure is identical, right? Look at the structure. 2, 2, k, plus 1, plus 1. So that's how you know. That's how you know a number is odd. And you do need to know that definition, so that's a definition you need to memorize. Here's a good question. Is 0 even, odd, or neither? What do you think? Take a few minutes and think about it. Let me know what you think. Is 0 even, odd, or neither? Hmm. Okay, now that you've thought about it, talk out loud. Talk out loud to yourself or to no one or to your group members or somebody and just kind of talk about what you thought about. Okay, now let's talk about it. First of all, if I'm being asked this question and I'm going to make a claim that it's any of these, then I would have to use these definitions up here to show that I'm correct. So that's a proof. So 0 is actually an even number. It's an even number. And the way you can tell is because I can write 0 as 2 times 0. 2 times 0 is 0, and that means 0 is an even number. On the contrary, it is not odd because I cannot write 0 as 2 times anything or 2 times something plus 1, right? Think about it. If I could write 0 as 2 times k plus 1, then that means that negative 1 is an even number, right? Here's the contradiction right there. That negative 1 is an even number. So that's definitely a no there. Contradiction lightning bolt. So 0 is definitely not odd. It is definitely even. All right. And how did I do that? I proved it using the definition. Like I said, don't believe it. Don't believe it. Prove it. Okay. So the other important thing is this. The set of integers is denoted by this fancy z. And it's the set of positive and negative whole numbers. That's what it is. The union of the even numbers and the odd numbers. So one of the nice things about the even numbers and the odd numbers is that they partition the set of integers, which means that if you have this set, then your number must be even or odd, which is really handy because that's like a binary relationship, right? You've got this infinite collection of numbers negative 10, negative 9, negative 8, negative 0, 1, 2, 3, 4, 5, 6, 7, right? You have this infinite collection, but you know for a fact that if you pick any number out of there, it's going to be even or it's going to be odd. One of the two has to be. Okay, so, all right, so here's some true or false questions. And what I want you to do again is just take a few minutes, think about it, think about each one, and then talk out loud about your solution. And don't forget this part. If it's true, then use the definitions to prove it. So if you believe that one of these is true, then you need to prove it, right? Don't take my word for it. And if it's false, then provide a counterexample. All right, so take a few minutes and think about it. All right, now talk out loud about what you were thinking. Okay, so now let's talk about this together. Let's see, the sum of two odd numbers is odd, true or false? If I add two odd numbers, do I get an odd number? Well, let's just try something. Let's practice, right? Let's see, two odd numbers, here, 3 plus 3, that's 6. That's an even number, so that's got to be false. There's a counterexample. There's a counterexample right there. um, in fact, the sum of two odd numbers is always going to be even. It's always going to be even. Actually, do I prove that over here? No, not yet. Okay. Yeah, I'll have to cram it in here. I forgot to leave myself some space. But I actually claim that the correct statement is that, oops, is that these numbers or the sum will be even, right? You believe me? No, don't believe me. You should ask me to prove it, and I'll do it right now. I can prove it. I'm not going to claim something if I can't prove it. So here we go. I claim that if you take any two odd numbers and add them up, you'll get an even number. That's my claim. And here's the proof. So what I'm going to do first is I'm going to specify two odd numbers. I'm going to label them. And remember what it means to be odd. It means I can write it as 2k plus 1, right? So I'm going to say n is 2k plus 1. That's my first odd number. And then here, I'll write proof just to be sure here. Here, proof. And then m, a different number, I'm going to write it as 2j plus 1. Now, I had to use a different letter because if I write it as 2k plus 1, then I'm saying that n and m are the same number. And that's not sufficient, right? I'm claiming that if you take any two odd numbers and add them together, you'll get an even. So I don't want to talk about adding the same two, or I'm sorry, the same odd number to itself. I have to be more general. So I picked a different letter. I picked j. All right, then let's add these together. And I'll actually write this over, I'll do it over here. N plus m is equal to 2k plus 1 plus 2j plus 1, right? I'm just substituting these in. And then I'm going to move some things around. I can rewrite this as 2k plus 2j plus 2. I can combine the ones, right? Now, what do you notice about this expression here, 2k plus 2j plus 2? What do you think anybody have any burning desire to do something to those three terms? You can factor out a 2. So check this out. I can write this as 2 times k times j plus 1. And now this is where you want to kind of like squint your eyes and like lean back and maybe, like just kind of look at it more fuzzily. But look at the structure I've got over here. The structure I have is 2 times some number. 2 times some number. Doesn't matter what that number is. It's a whole number, or it's an integer, I should say. It's 2 times some integer, which means that that number is even. This is an even number. There it is. That's an even number! Exclamation point. Even number. So what I've now shown through this chain of true equalities, let me highlight it here. This chain of true equalities is that n plus m is an even number. So there you go. I've just proven my claim. And I proved my claim just by using the definition of even and odd, right? That's all it is. It's just using the definition and some basic arithmetic. So it is true that the sum of two odd numbers is even. Okay, now let's go to the next one, right? Let's go to this one down here. The sum of an odd number and an even number is even. What do you think? True or false? True or false? Well, if I take an odd number, I'm just gonna go straight to the definition. Here's an odd number. And here's an even number. And if I add those together, I can write it as 2 times k plus j plus 1. That's an odd number. That's an odd number. So if I take an even and an odd, I'm going to end up with an odd. And that makes sense, right? It makes sense because if you look at these definitions here, I can combine the two even parts, right? But there's always going to be this little extra one hanging out if I have an odd number in there. So if I add an even and an odd, I'm going to get an odd. But if I added two odds, then what happened up here was the ones combined to form an even number, too. That's the key, right? So that's why it worked. All right, so this one is still false. This is false because if I take an odd and an even, I get an odd number. There's the proof. How about this one? The product of an odd number and an even number is even. What do you think? That one's actually true. That one is true. And again, if it's true, then I should prove it. Don't believe me. Oh, I forgot to put my little end of proof symbol up here. There you go. A little like boxy square is used to indicate the end of a proof. It's like your little victory lap, right? Woo! Okay. So let's prove this one. I'm claiming that the product of an odd number and an even number must be even. Don't believe me, though. Here we go. Let's prove it. I'll say let n be 2k plus 1 and m be 2j. There's an odd number and an even number. Then I'm going to multiply them together. N times m is equal to 2k plus 1 times 2j. And then this is, again, one of those times where you got to kind of squint your eyes and think about the structure you're looking at and think about the associative property of multiplication, right? I can write this as, I can move some things around and I can write it as 2j times 2k plus 1, right? There you go. But look at this. Look right here. This is 2 times some number. Here it is. It's 2 times some number, which is even. That's an even number, right? So this whole thing right here is an even number. And there's the proof. All done, right? So easy, quick and easy proof. You just had to use the definitions of easy, definition of even and odd. Okay, all right, so these are the theorems that are not in the book, and you do not need to memorize these theorems. I want to emphasize that. You don't need to memorize them, but you should try to work with them enough that they become familiar, because these are the theorems that help you do a lot of arithmetic more easily, in particular division. So this theorem is a very important one. The book uses it without mention. It says for any whole numbers a and d, if d divides a, and n is any other whole number, then d divides n times a. But more intuitively, I would say it says this. In other words, if a number divides another, then it divides all multiples of that number. That's a critical thing to know, because what it's saying is that if you know some number divides another, then it has to divide any multiple of that number. I'll give you an example. We know that 2 divides 6, right? 2 definitely divides 6. So because of that, we know that 2 must also divide 12, and 2 must divide 18, and 2 must divide 24. And what's 12, right? 12 is 2 times 6. 18 is 3 times 6. 24 is 4 times 6. These are all multiples of 6. And so what this theorem says is that if you know this part is true, then you know it's true for all multiples of that number, which is really handy, right? So that's all you need. So the book uses this but does not mention it. And these are the big ones. So these theorems, like I said, you don't need to memorize these, but they're very, very helpful and they're very, very important. And we're going to practice using them on the activity. So just take a minute and look at those and think about those, okay? Oh, let me get my little thinker up. Here we go. Okay, now let's, actually now talk out loud about what you read. Try to say this in your own words. Try to say this in your own words. Okay, Now let's talk about them. One thing that I've noticed is students tend to struggle with what numbers are going where in these theorems. So try to keep that in mind. What this is saying, let's look at the first one. The first one here is saying that if D divides some number and D also divides another number, then D divides their sum. So I'll give you an example here. I know that 2 divides 4 and 2 divides 18. So 2 divides 4 plus 18, oops, plus 18. In other words, i.e., 2 divides 22. So that's what this theorem is saying right here. And that works for any number that you know divides these two numbers, a and b. All right, so that's the thing. Similarly, the second one is very similar, but it's basically saying if d doesn't divide one of those, then it doesn't divide the whole thing. So let me do an example of that here. Actually, let me check something. Yeah, okay. Check something out here. Wait 1 second. Oh yeah, okay, almost done. I'm just like, man, this is going on a little bit longer than I expected. Okay, so let's do this one. If D divides A and it doesn't divide B, then it can't divide their sum. So how about this? Let's do, I know 3 divides 9, but I also know that 3 does not divide 10. So that means that 3 does not divide 9 plus 10, or in other words, 3 does not divide 19. Oops. There we go. So that's what that theorem is saying. 3 does not divide 19. Now, the reason this is really handy is because this lets you determine if numbers are divisible by certain numbers more easily. And we're going to see that in the next lecture, actually. But that's why we're taking the time to learn this, and why I was bummed that the book omitted it, because it's very helpful to do mental computation, actually. Okay, this one is referring to differences. In fact, the last 3 all refer to differences. And this one says if D divides a number and it divides another one, and this is just to ensure that everything stays positive, A greater than or equal to B. You could almost forget about this part. It just means we want to stay in the positives. Like, okay, we don't want to deal with negatives right now, just positives. Then it must be the case, let's look at the first one. Here we go. If D divides A and D divides B, then it divides the difference. So it divides their difference also. Let me try to give you an example of that. Delete. Okay, All right, I know that 5 divides 25, and I know that 5 divides 10, and I know that 25 is greater than or equal to 10. This is that part right there, this part right here. So 5 divides 25 minus 10, or in other words, 5 divides 15, which is true, right? 5 divides 15. So that's what that theorem says. And this is the only reason that we need to have we just want positivity. That's why we do that. All right, now you can probably guess where this is going in the next one, right? Because it's similar to A and B, parts A and B. This one right here says the same thing kind of, except if D does not divide the second number, then D does not divide the difference. So let's do an example of that. Let's see. I know that, how about this? 6 divides 64, right? Oh, no, it does not divide 64, my bad. Let's see, I'll stick to something easier. 6 divides 36, and 6 does not divide 13, right? It doesn't divide 13. So, oh, and I should say, and 36 is greater than 13. And 36 is greater than or equal to 13. So 6 does not divide 36 minus 13. Or in other words, 6 does not divide, what is 36 minus 13? 23. And it's true, 6 doesn't divide 23, right? And then this last one is very similar to the one above. I'll leave you to do an example on your own. It just says if D doesn't divide the first number, then it also doesn't divide the difference. So it's the same thing, except you've got to pick a number, for example, here that 6 doesn't divide, and then pick a number here that 6 does divide. You could do it pretty easily, right? I'll just do it here. Just increment this. 6 does not divide 37, but 6 does divide 12. So that means that 6 does not divide 37 minus 12, which it doesn't. Okay. Oh yeah, so now true or false. So this is going to be another door moment, right? So just take a moment and think about if these are true or false. Let x and y be whole numbers. Hmm. Hmm. What do you think? All right. Well, now talk out loud about what you think. Talk out loud to yourself, to a ghost, to your cats, to your dogs, to your friends, to your group members, hopefully. And what do you think? What were you thinking about? Hmm. All right. Now let's talk about them together. This first question here says, if 5 divides x plus y, then it has to divide x and it has to divide y. So what I do when I see true or false questions like this is I'm just like, okay, wait a minute here. Okay, say it out loud a bunch of times, think about it, rephrase it in my own words. So the way that I see it is this says, if 5 divides a sum, then it has to divide each term in the sum. If 5 divides the whole sum, then it must divide each term in the sum. That doesn't sound true to me. I'm pretty sure that's false, but don't believe me. Don't believe me. If it's false, then I should be able to find a counterexample. Let's check. Okay, how about this? I know that 5 divides 10, but 5 does not divide 3, and 5 does not divide 7, but 3 plus 7 is 10. So basically 5 is dividing 10, but that doesn't mean that it has to divide 3 and 7. So this is definitely false, right? Definitely false. Okay, let's look at the next one. The next one says, if 3 divides a number and 2 also divides that number, then 6 divides that number. That one is true. That one is true, right? But why? Why? If it's true, then we should be able to prove it. Well, let's prove it right now. Okay, what does it mean for 3 to divide a number? Hmm. What does it mean for 3 to divide a number? I'll give you a moment to look up that definition again. What does it mean for 3 to divide a number? Hmm. Hmm. Oh, that's right. It means that I can write that number as a multiple of 3. So let's go ahead and do that. We can write 3 as, or sorry, we can write x as 3k, and we can write x as 2j also. Okay, so what that means is that x can be written as a multiple of 3 and x can be written as a multiple of 2. So that means that both 3 and 2 must appear in the prime factorization. So if both 3 and 2 appear in the prime factorization, then we can write x as 2 times 3 times some other number. But this is 6. That's 6. So that means that x is equal to 6 times, J, K, L. But what does this mean? This means that x is divisible by 6. This means that 6 divides x. And there we go. So that one is true. That's true because of the prime factorization, right? Okay, now let's read this next one. The next one is interesting because it kind of says the same thing as number 2, but it's also got this little asterisk there, so it makes me think something is up, right? Because something is up, and we're going to refer to this again in the next lecture. That's why that asterisk is there. Um, but this one says if 3 divides a number and 6 divides a number, then 18 must divide that number. Is that true? No, that one's false. That one's false. There's something different about this one and the one above, right? There's something different, but I can find a counterexample pretty easily. For example, 3 divides 12, and 6 divides 12 also, but 18 definitely does not divide 12. Definitely doesn't divide 12. So this is definitely a false statement. That's not true. But what went wrong? Because up here, we were able to show that it is actually correct, that it is definitely true. What went wrong? What did we rely on in part 2? The prime factorization. Something about the prime factorization is important here. And we'll come back to it later, but I'll give you a clue, and this is something you can ponder, when you're in the shower or whatever. There's there's an important distinction between how these two numbers are related and how these two numbers are related. So think about that. And if you can ponder that enough, that'll lead you to the answer. Okay, last but not least, if 5 doesn't divide a number and it doesn't divide another number, then it can't divide the sum. That one is actually definitely not true, right? Definitely false, because we saw that before, right? We saw that when we did the example for this one. 5 doesn't divide 3, and 5 doesn't divide 7, but 5 does divide 10, which is the sum. So this is a false statement. There we go. Okay, now that's it for lecture 11B. Let's take a look at the activity and see what you're going to do. Let me pull it up here. Where are you? Come here. Okay. So, all right. So what I did here was I first repeated those theorems that we just explored in the lecture, okay? And what you're going to do is you're going to use those theorems to show some various things. And it actually tells you exactly which part you're going to use. And this is going to kind of lead you into the next lecture, because once you realize what's going on here, you'll realize that it's going to be really helpful to help us determine divisibility. And just a little clue here, I picked these numbers on the right side very, very specifically because they're very suggestive of what you should pick. You'll see what I mean. But yeah, so just think about the numbers that are chosen here, because they're chosen very, very to make things nice and make things edifying, as you'll see. But that's all it is. You're just going to use those theorems to show these are true, or yeah, to show these true statements are true. Okay, so I think that's about it. Yeah, so the next lecture is 11C, and then we'll finish chapter 11. 11C is when we do all of the divisibility tests, all right? So I'll go ahead and say bye, and I'll see you next time.